Okay, so it's time to start. And as you all know, there's no class this Thursday on Halloween. And but there still is homework due, and that homework will cover what we do right today. So I just want to make sure, is this mic working? Can you hear? Well, okay. So also I just want to say that there's no office hours either on Thursday. And I'll be there today, but I won't be able to be there on Wednesday, but there'll be an instructor on Wednesday anyway to help you. So, but if you feel like working on your homework that's due Thursday this afternoon and have any questions on it, feel free, just come by and get it out of the way. Come by the office hours, and that'd be great. So let's do the last two chapters we're going to do on this section. That's chapters 36 and 37 today. So remember where we left off. We were talking about, okay, so we're on page 163 right now. And the last thing we did was we did this, we're talking about multiple regression, having more than one X predictor variable. And the first thing we did was we used an F-test or a chi-square test to test the collective effect of all the slopes acting together. So we wanted to see if there was anything in the model. So we tested whether all the slopes were zero, the collective of all of them were zero, or not. So if we rejected that null, it means that not all of them are zero, so at least one of them is non-zero. So at least we have one slope that has some signal and is making some decent prediction for our y value. So then the next step, what we're going to be doing today, is once we've done that and we see there's something in our model, we're going to do tests on the individual slopes in the model. So let's look at this. So what I said is once we find out that at least one of the slopes is significant, we can then do individual, now we can do Z and T tests for the individual slopes in our multiple regression model. The same way we did for simple regression, but we have more information because we're looking at the effect of all the slopes together. So our degrees of freedom are going to be adjusted when we do a t-test. But let's first just start off with the z-test, okay? So let's look at this. And so now we're going to do these significance tests for the individual slopes. And if we're going to start off using a z, on the next page we'll use a t. So here, right here, let's look at this. This is the overall test we've already done. So this is the overall chi-square test. We also did an F-test. We'll look at it on the next page. So this is the overall chi-square test right here. And of course we saw this was significant, which means at least this here, right here, means what? We rejected the null and we said at least one of the slopes, maybe both. Remember what our model is. It's the same example we did before. Here, where's our model? So you can remember. Here it is right here. Okay? So we tested this and we saw that at least either homework or exams or both is significant in this model. Okay? So at least one of our slopes is significant. Maybe both. So now it's time to test them to see which one. So we're going to look at these individual slopes here, and we're going to use the computer to do the standard errors for us because it's too complicated with multiple regression because we have to adjust for the other x's in the model. Remember, these are not the same slopes that we got in those simple regressions. So now let's look at this. And of course, we have this. Should be very easy for you because we already know that a z statistic is this. You're going to have the observed slope minus the expected slope over a standard error for the slope. So our observed slope, we're going to test the homework first. Let's test this one. Let's look at this one. And it gives us the slope right here, right? So now we're going to do this z-test. A z goes along with the chi-squared. A z-test for the individual slopes. All right, so this is B0. We're not going to test that intercept. We're just going to test B1 and B2. And B2 is already done for us. We can see it's significant. So now let's look at, so these are the same slopes here. This is our observed slopes right up here. So here's our homework slope, the observed. So that's our observed slope right there. We're going to do the z-test. Minus the expected under the null. And what's the null? The null is going to be what? Where did we put our null? Right here. That the slope is 0. So it's minus 0. That's what we'd expect under the null. Okay? Over the standard error, which will be given to us here because they're too hard to calculate on without the software doing it for us in multiple regressions, so you'll be given them. And so there's the standard error. And we'll get this z statistic of 2.27. So that's our z. We can put it in right there. All right. So now we're just going to get a p-value for it. All right. Now, first of all, let's look at our alternative here. It's not equal to 0, so that means we're going to have what? A two-tailed test. If it was directional, if we put greater than equal to 0, it would be a one-tailed test. But this is a two-tailed test here. All right. So now here we are. And this is our normal curve. Here's our z. 0 is in the middle. 1, 2, 3. -1, -2, and -3. And this axis right here, right underneath it, matches up with, I'm matching it up with our homework slope. This is the homework slope. Under the null, we'd expect it to be 0. And what did we get? We actually got this slope. And we said when we match it up with the z, we get 2.27. So let's draw 2.27 in. So that's 2.27. And that's what matches up on this slope axis with our, it translates to this, 0.1641. So that tiny little slope that looks so small actually is a big z-score, as you can see. Why? Because our standard error is even smaller. So that's how we got such a big z. That looks like a small slope, but compared to the standard error, it's quite big. And what's our p-value here? Well, between 2.27 and -2.27, that would be between -0.1641. I looked it up on the calculator, the p-value calculator, and it's 97.7 rounded to 1 decimal place. So that means we're doing this two-tailed test. That means these two tails together is our p-value. So mark z and p. Okay, so our p-value is equal to 100 minus 97.7%, which is 2.3%. That means, so that's what we put in here. Because it's two-tailed, we're using both sides. And so that means that if we were doing a one-tailed test, we'd divide that in half, right? And we'd have 1.15% there and 1.15% there. Okay. Any questions on that? So what are we going to do? Our conclusion, obviously, is what? We're going to reject the null, because our p-value at the 5% level, reject null, and conclude the homework slope is significant, and so we're going to conclude what? that there's very strong evidence that in the population, the homework slope, so I'm using the Greek letter here, beta, in the population, that slope for homework, this is what we got, the B1, beta 1, is what? It's not equal to 0. That we have some information there that's valuable in predicting the final. So that's the idea. Any questions on that? All right, so now we'll do the same thing with the, and you can see that it's done, the computer did it for you, and they got even stronger. Look at the slope for the exams. We can compare them because they're basically in the same units. And this means a 1 point increase in your exams holding for people who have the same final. A 1 point increase in somebody's exams for people who have the same homework. So you and somebody else who have the same homework scores, if you scored 1 more point higher on the exam, that would mean on the average, you'd score almost 0.6 points higher on the final. That would be our best prediction. So that's stronger than the homework slope. And you'd think that, that exams would be a better predictor than homework of finals. And so we got a smaller p-value here, etc. Okay? Now we're going to do the same thing with the t and the f. And it will give us very similar results. We have a large sample size here. So let's see what we're doing here. Okay, so here's our overall f-test instead of the chi-squared. And we already did these. We did this one on page 159. Excuse me, and you can look, and I'm not going over it because we already did this on page 158, the chi-squared. And both the p-values are tiny, right? And we get a much bigger looking statistic just because chi-squared is centered at its degrees of freedom instead of at 1, like the f. We went over that. All right, so this is page 151. This is the overall f-test for the collective effect of all the slopes. And again, this tells us that at least one of them is significant. We're doing the same thing, but now we're going to use t-tests here because f and t go together. If we're going to worry about the error degrees of freedom here. So this is a t-test for the individual slope. So we're doing the same exact thing just with t instead of z. So what do we have to do? First of all, we're going to change. We're going to use a slightly bigger standard error, slightly bigger by that factor. That's what we're going to do. So we're going to use SE plus, and SE plus is slightly larger. Than SE by that factor. That factor is bigger than 1. Okay, and as you can see, here's what we're going to be using this time. A slightly same, of course, observed slope, but a slightly bigger standard error. And we're going to calculate the t. So let's do that. So we do the same thing, the observed slope minus the expected, but now we just use this slightly bigger standard error, and then we get this t. Okay, but the big difference is going to be this t curve is going to be different. It's not going to be so much different because we have a lot of degrees of freedom here. It's going to be what? How do we get these degrees of freedom? Now, the degrees of freedom, it's not n minus 1 like you're used to, or n minus 2 necessarily. It was n minus 2 for simple regression, but now it's n minus the number of parameters in the model. That's what it always is. But now we have to be careful. It's always n minus the number of parameters in the model. So if you have one parameter, just estimating a mean, it's n minus 1. If you have 2 parameters, when your model is a line, what this is, the error around the line. 2 points determine the line, n minus 2, and then you have some scatter around that. And now we're dealing with the plane. We have 3 parameters. So it's n minus 3. Okay? There's your n. There's your error degrees of freedom. And there's your model degrees of freedom. Okay? So this is 107 minus 3. Let's write that down. So the degrees of freedom, we have to use this degrees of freedom here. The degrees of freedom is n minus p. So in this case, it's 107 minus 3, which is 104. So now we have to look at this t-curve right here with 104 degrees of freedom. So it's going to be very similar to the z-curve. That's what this is. And it's centered at 0. Okay, so this will be our t, just like we did with the z, and this will be, of course, the homework slope. So now this tiny little slope, where does it match up to? It matches up to 2.24. Okay, so let's do this. 1, 2, 3. So that's where it matches up now. And then we look between 2.24 and negative 2.24. And remember, on the t-curve, it's flatter in the middle and has fatter in the tails. So this middle area is going to be smaller. So instead of getting 90, it's not that much smaller. Before we got 97.7, here we get 97.38%. And so these will be a little bigger, right? So now our p-value is, so how do we compute our p? Our p is going to be 100 minus 97.38, because it's two-sided again, and that's 2.72%. So let's fill this in here. This 2.24 goes here, and this 2.72 goes there. Okay? So we always get a bigger p-value with the, instead of getting 2.3%, we have 2.72%. And in our tails, if we divided this up, what do we have? Instead of 1.15, we have 1.36% in each tail. Now, so we just answered that question. Is the p-value using the t-test always bigger? Yes, because p is the area of the tails, and they have fatter, t has fatter, f and t have fatter tails. There's more uncertainty. That's why we need stronger evidence to reject the null. So yes, it's always bigger for everything else being equivalent. So that's the idea. Any questions so far? Let me see if I left anything out. Let's just remember what our null is here, and why we're doing the two-tailed test is because for this right here, our null and our alternative, let's just write it down, is what? The null is that beta 1 is equal to 0, and this is beta 1 is not equal to 0. It would make a lot of sense to say it's greater than 0, because you would think that doing the homework helps you on the final. So I could I think if I could easily change it to that. With the individual slopes, remember, you can get a positive or a negative. We get a positive. We could fall on this side or this side. So we can make a directional alternative and have a one-tailed t, in which case we'd have 1.36, a smaller p-value. Remember, the chi-squared and the f only give you, they're the sum of squares, so they can only be positive. So they're always equivalent to the two-tailed. Okay. Now, let's see what else we want to do here. Okay, so now we're just going to look at confidence intervals. We can do confidence intervals on the individual slopes. So this is exactly like we did before with the confidence intervals, except that's basically the same thing. All right, so confidence intervals for the individual slopes using t. Well, we just did this t, so why don't we do the confidence intervals so we can see how they match up. Now, remember what the confidence interval is. So the confidence interval is going to be what? A 95% confidence interval, that's what these are. We're looking at this, will be our sample slope, plus or minus what? The critical value corresponding with 95%. What does that mean? Here we are on the t curve. The same curve, it's t curve with 104 degrees of freedom. So that's where we are. And we want the critical value for t that has 95% in the middle. Here we had 97% in the middle, so we don't want to go out that far. So what do we do? So this is t star. This right here is t star, the critical value for 95% in the middle. So the value of t that gives you 95% in the middle for this particular curve. So let's do that. What is it? 1.983. It's almost 2. So close to 2 you can barely tell it apart. Negative 1.983 and positive 1.983. Okay, so that's what it is, and that's 95%. Now, so let's write that down here. It's plus or minus 1.983 times what? Times the standard error. So that's times this. And that's what gave us these limits. So in other words, I don't want to get you get too confused here, but here we are on the t, and I'll just line it up. We just did this. Our actual t that we got, this is the critical value. Our actual t was what? 2.24, right there. And that's what lined up with this, with the t, this is the t curve, and this is our slope curve. Okay? So it's right outside. So it's outside that limit. That's why we rejected the null. And you see, when it's outside that limit, if we go over to its lower limit, doesn't include 0. You go over 1.983 standard errors, and of course, if you went over 1.93 standard, you'd get to here. But now we're bigger than that, so we get that little distance right there, which is that. And then we go up. So we didn't include 0. So do you see how do our confidence intervals agree with our significance test? Yes. Because this confidence interval does not include 0. So that's the same as our landing beyond. This is 95%. So this whole thing is what? This is 2.5% in this direction. And this, all the way here, from here this way, is 2.5%. Our t has a smaller p-value, right? And if you double it, it's only 2.72, so it's less than 5% because it's beyond the critical value. So it's the same as rejecting H naught, that our slope's 0 in the population, with a two-sided test at significance level alpha equals 0.05, same as P equals 5%. At significance level 5%. It's we got less than 5%. So you can see how those two things are equivalent. Same with the Z. So we can do the same thing with the Z. It's probably something easier because there's just one critical value. You don't have to have a separate one for each degrees of freedom. It's just one. And we've been calling it 2, but it's actually 1.96 here. So our 95% confidence interval is going to be the same thing. But now instead of T star, we're using Z star. And you see that's a little bit narrower. That's always wider. We always get wider confidence intervals, more uncertainty with the T. 1.96 times our standard error, which is slightly smaller too. So our confidence interval is slightly narrower. And this is it. So we can draw this one. This is easy. This is the Z that we're familiar with. That says homework slope. This is in units. This is unit free. This is in units of what point per point of final per point of homework. And so we go 1, 2, 3. The T, they look very much the same, the Z and the T curves. And in fact, it's in this drawing, I'm really not as close to 2. I should be a little bit lower, but it's so close to 2, we're still going to draw it as 2. And so this is negative 1.96 and positive 1.96. And that's 95%. We usually just round to 2. And, of course, again, this is 2.5%, 2.5%. And now, if we wanted to draw the 1641 in here, it matches up with our Z-score of what? 2.27. So we can do that if you want. There's 1.9. I hope I don't. Here, I'll just draw it in like this. So that's 0.1641. And on top here, it was 2.27. Okay, and of course, again, we rejected the null, and it's the same thing as we went, see our lower limit, if we went down this way and that way, it doesn't include 0. So that's the idea. Any questions? I like to do the same thing over and over again in different contexts, just so you get a fuller understanding. Repetition's good for learning. Okay, so now we're going to, now that we did all that, we're going to say, okay, look, in both our models, we have really significant slopes, okay? So we want to include them both in our model. Could we improve our predictions, the question is, by adding a third variable? So maybe we want to make better predictions. So can we improve them by adding a third variable? So that's what we're going to look at now. Adding a third variable to the model. And when you're actually doing statistics, this is going to be a very important question because you want to get the best predictions you can get. So why not add more information here? So let's the Z and T test showed that both homework and exam slopes were significant in this equation right here. So let's keep them both in the model, and maybe we can do better by adding a third predictor. And so I'm wondering if the third predictor would significantly improve the prediction for final. Okay? Now, I want to see if R squared is going to go up. Do you remember what R squared is? R squared is the correlation between your predicted finals and your observed finals. So it's the best, the most direct measurement of how close our predicted finals are to our actual finals. To the actual ones we got in our sample that we built our model on. Okay. So now, I said I added labs as a third variable. Do you think that would make our predictions better? Well, it will make our prediction, will make R squared go up. Will our predictions be closer to our sample, to our model? Don't you think they would be? Because the more information we add, the more variables we put in, the closer we can get to the actual sample. If we put in 107 predictors, I could put one in for every single student, a 0, 1 variable for every single student, and I could have no error. No, I could exactly predict everybody's finals. Of course, it wouldn't do very well predicting another random sample. Okay? But the R squared would go up. So if I add labs as a third variable, how do you think it would change R squared? Well, it has to go up or stay the same. It can't go down because it's going to make our predicted finals closer to the sample. You can think of it this way. We're putting more information in the model, so we're going to be able to, it's going to make R squared go up. Okay? If R squared, if labs, our third variable, if labs are correlated with finals, it has to go up. Because it gives us a bet, if labs give us some information about finals, it has to go up. Whether it's negative or positive, it's still going to go up. It's going to give us a better prediction. Could it stay the same? It can't go down. Even if labs were negatively correlated, that would still give us a better prediction, right? And R squared's always positive. It just measures how close our predictions are to our actual ones. Could R squared could it ever just not change R squared? If our third variable is correlated with Y, then R squared's going to go up. But what if I added something that was completely uncorrelated? Let's say labs had nothing to do with finals. R squared wouldn't go down, but it would stay the same, right? So let's write that down. If labs are uncorrelated, if the correlation coefficient between them is 0, which it would be very unlikely, if labs are uncorrelated with Y finals, then it's not going to do anything. R squared will just stay the same. Okay, so adding a variable to a model will always make R squared go up in real life, because you never see a correlation that's exactly 0 in real life. But if you saw one that was exactly 0, it would stay the same. But what you're always going to see if you go out to enough decimal places is R squared is going to go up. So here I have 3 parameters, B0, B1, and B2. This is the model we've been looking for. Now I add labs. That gives me another parameter, which is going to make R squared go up, because I have B1, B2, and B3, and the intercept. So where am I looking? This is very small, but you have it at home. This is where I'm looking. R squared went up, but very slightly, just in the 4th decimal place. I can zoom in a little bit. Just here. Boy, you can't, sorry. That's very hard to see now. Ugh. Yeah, it just went up from 0.3841 to 0.3842. So is that a better model? Is that a better model? You have to be really careful, because when you increase, well, you're putting in more information, but you're also putting in more random error. Every time you add a parameter, you're putting in some more random error. So you have to weigh those two against each other. So check the errors. Look what happened to the errors. R squared went up, meaning that our predictions look better, but our error, look at this, our error went up too. We have more error. So it really isn't a better model. R squared went up, which is good, but so did our errors right here, as measured by the SD plus errors. That went up too. So why? How could they contradict each other? How could more information be bad? Well, because it adds more random error. So in general, you have to be very careful when you're adding parameters to a model, because they also introduce more error. So adding a parameter, even if it makes R squared go up, is not necessarily a better model. So adding parameters puts more information into the model, which looks good. You get more information inside the model. So that will make better predictions. But it also puts more random error in. So there's a trade-off. And if the error goes up, you do not want to include it. Let me go back a little bit so you can see that. Okay, so adding parameters puts more info into the model, but also puts more random error in the model. So R squared did not improve enough to warrant adding a 3rd variable. It just didn't, because we got more error. So if you see more error, you're also going to see a lower p-value. It's not a good model to do. It's not a good. You could look at R squared, but as long as also everything agrees. More R squared means better predictions. You also want less error, less p-value. And it's tricky when you add parameters. Okay? Now look what else happened that's really, remember, what did we have here? Right here we have significance for homework. When we added labs, all of a sudden we get this much bigger p-value. It went from 1.36 all the way up to 8.47. All of a sudden it's not significant. Now I didn't show you, but labs by themselves were significant in the simple model. Now, not at all significant. So what happened? And you have to be, I tell you, when you put more variables in a model, things can get complicated. Okay, labs is not significant, as you can see, but it was in the simple. But why did adding labs make homework change from being significant to not significant? See? Could this be a mild case of our, remember when I talk about the left foot, right foot syndrome? They're great predictors. Each one is a great predictor. Left foot's a great predictor of your height, the size of your left foot, and so is right. But if you put them both in the model, they can both become insignificant. It can do really, because there's almost any linear combination, any combination of the slope of the two of them together is going to give you a good fit. So it has huge error bars around that. They don't know which that fitting program doesn't know which combination to use. So they can both become insignificant. All right. So let's check the correlation matrix. So what we want to check is how labs and homework are correlated. And they have a very big correlation. This is what we're checking right here. Yes, they're very correlated. This means both slopes can be insignificant when both are included in the model, even though individually both are significant. That doesn't mean we should throw them both out. That absolutely doesn't mean that. You want to include one, just not both. We can't do a good job of estimating how much of the prediction should be based on one or the other because they're both predicting the same thing. So it's saying, hey, I have error bars on both of them, but the model itself will have a very good p-value. You just won't know which one to use. Okay? So, yes, they're highly correlated and very important. Do not include, people do this all the time and you get screwy results. Do not include two variables that are highly correlated into your model. Just choose one or the other. Okay, so let's zoom out a little bit and make sure. Let's just summarize a little bit what we said here. So, that was one point we made, but another point was what? That if two models have different number of parameters, and you're always going to be comparing models. You're going to have the same data set, the same sample, and you're going to say, hey, what happens if I add more parameters? So this is a warning. If two models have different number of parameters, because you're trying to make a better model, so you add parameters, okay? Don't compare them using just R squared. You can look at R squared, but don't compare them using just R squared. It's a good thing to look at, but really you also have to make sure, you also have to use, you must also use the errors, compare the SD plus errors, and the p-values. And they should all agree. And they should all, I think if your errors go down, well, your R squared is always going to go up. So that's why it's not good just to use R squared. You want to see how much it went up, and then make sure that these go down and this goes down. Okay? So the model that has less error and lower p-values is better, obviously. That should go down, less error and lower p-value is better, lower p-value is better to fit. What do I mean better? You're comparing, the null is always some simpler model, like the null we've been using is that the slope, there's nothing there. It's just all chance. Okay, so you're fitting some other model that you think has some predictive value. So the lower your p-value, the more evidence you have that your model has some information in it, as opposed to just chance. So that's what I mean. It's a better model. Otherwise, that's what I mean, that it's predicting better than just chance. Because remember, that's what the p-value tells, how likely you'd see that result in your sample just by chance. And if that likelihood, that p-value is really small, then you reject that it was just due to chance and you have some meaning in your model, some significance. All right, now what are we going to do? So what's the conclusion here? I know I'm spending a lot of time on this model building stuff, but you're going to see this a huge amount. And there's whole courses on this, how to choose the best model. So I just want to give you some pointers. And so what should we do? We can't put them both in the model homework and labs, so which one should we use? What's the conclusion? And don't drop them both out. Instead, compare the R squared, and you can do the p-values and the whole, compare the R squared for predicting finals from exams to predicting finals from exams and homework. So that's this one. This is the homework one. So we're going to do the one that includes homework. They both have parameters equal to 3, to the one using exams and labs. So this is labs. We're including labs. Now we're comparing the same number of parameters, so we can use R squared, because R squared will be consistent. If you're comparing the same number of parameters, if you have a higher R squared, you're always going to have less error and lower p-value. So then it's fine to just look at R squared. And so now we have to, let's look at this. And so we have 3, and which is the better model? Let's look at this. Well, this has a higher R squared, and it should also have less error, and of course it does. So this one has more error and lower R squared, and this one has less error and higher R squared. Okay? So which R squared is higher? Homework. So our conclusion is the homework model's better. And you can see that homework, look at this, that homework has a bigger slope and it's more significant. This is more significant. It has a lower p-value. Lower p-value than labs. Okay, so the homework model is better, and in general, the takeaway is when comparing models with the same number of parameters, like we are here, the higher R squared will always have the lower error. So it's the better model. Okay, so that's the idea, and you're probably, I'm sure you're going to be doing, there's a lot of software programs that do these model fitting. They add parameters, they either start with a few and keep adding them, or they'll start with lots of parameters and start dropping them out. And so there's different ways to approach this problem, and you're going to see something called the adjusted R squared, which you can always use, which it's just, if anybody's interested, I can explain that to them, but you've got a lot on your plate already, but that's something that's very easy to explain from what we've done. I just don't want to add another thing to the mix right now. Okay? All right, now I just want to draw your attention to this SD plus errors. So look at this SD errors here, right? And the SD plus errors, which is a little, that we've been looking at before. So what is going on? I just want to remind you. So the SD plus errors we use for the F when we're using the F and T, and this we generally use when we do the Z and the chi-squared. And how do they relate? Well, we went over this in chapter 23, the basic definition of the SD errors, just to remind you. And this is what we did. We used a little r, but it's the same thing. Okay, that's what we did. And what's the SD plus errors, just to remind you? So that is just the SD errors. For this case, with just one, when we're testing individual slopes over n minus p. Actually, always, because I'm putting the p in here. Okay, it's just a little bit bigger. That's all we're doing. Okay, now, I think you're going to like the next section that we're going to do. It's going to be a non-parametric way to do these tests, to test the null that r is equal to 0, or all the slopes are equal to 0. So, as I was saying, we're now going to look at a whole new way of doing these significance tests using re-randomization techniques. So what is that? So, randomization test, or the re-randomization test for regression, is another way to test, you use it to test the null hypothesis for regression, in this case, that r is equal to 0, which is the same as the slope is equal to 0. Those two are equivalent. We're going to first look with just one slope, and then we're going to look at multiple regression with more than one slope. All right? And it's to test that against the alternative that r is not equal to 0, same as the slope is not equal to 0. So, remember, these tests that we've been doing are called parametric tests because the parameters depend on defining the distributions that the samples come from. So they all depend on the assumption that the data that our models are independent, that the errors are independent with equal variability and follow the normal curve. In other words, we called it IID. The errors are identically distributed, independent, identically distributed with normal 0 sigma squared. Now, we don't have to use that for these. We don't have to worry about this. We are just going to enact a random process. And the randomization test has the advantage of not requiring all those assumptions. It's a completely new way that I haven't shown you of doing a significance test, a distribution-free way. That's why it's called non-parametric. It doesn't depend on parameters of defining any type of distributions. So what are we going to do? Instead of computing a test statistic by estimating those standard errors, assuming theoretical underlying normal populations, like the TNF does, or large enough samples that the central limit theorem kicks in, like the normal chi-square test do, we are going to use computer simulations to produce our own distributions, empirical distributions, randomization distributions. Okay, so we're going to enact the randomization process. So here's how it works. Okay, so we're going to use the same example. So we found this R in our sample, right, of 107 students. And we got this equation. And this was our null and alternative. We're going to keep it. Now, what we're going to do is we're going to assume the null. Remember, you always assume the null, so we're going to create our own distribution of the sampling distribution of R under the null by enacting the null, that it's just, there's no correlation. We're just going to randomly assign finals to homework. So we have 107 students, but these are the actual first, I'll just show you how it works with the first 20. So these were the first 20 students, their actual homework scores. I copied it from the roster. And these are their actual final scores. So this is the way they're actually paired up. So each student, that's his homework, and that's his final. And from that, so these are the actual homework final, X, Y pairs. And from this, we got an R equal to 0.3926. That's what we got. Okay? But what we're going to do now is we're just going to randomly scramble them. We're going to let the computer do that. So it's just going to randomly pick, let's say it got there 64 for this person. And then it will throw that one out, right? And then it'll do it again. And let's say it got 46 for the next person, all the way. So it's going to assign a scrambled random final to each of these homework scores. Okay, and let's say it got all the way down. Let's say it got to 60 here. So now what it's going to do is, so let's say it did that for all 107 people. So it has 107 of these. What are these? These right here are the X and randomly assigned Y, scrambled Y. Okay, and it's going to compute R for that, the correlation coefficient. Then it will do it again and again and again and again. And it will look at how likely it is to get R observed R. Do any of these randomly scrambled, R's produced by randomizations, how many of them are as big as R observed R? So what we're testing here, so I say imagine putting all the final scores inside a box and then randomly choosing one and assigning it to student 1. The next chosen final would be assigned to student 2, etc. Then we'd compute R between the 107 homework and scrambled final scores. So this program, this is computing the absolute value of R, which you're going to see. But the computer, I'll show you one where it computes little r. Okay, so here there's the same because R was positive. Okay, so what are we doing? We're just testing whether R observe, this is our observed sample, R equal to 0.3926 is much different than the R's we get by random scrambling. Than the R's we get by randomly scrambling those finals and just assigning them. That the null says it's not going to be different. So we're going to see, is it different? Well, let's do it. So let's say we did that 1,000 times, that process. So we got 1,000 R's. We'd have 1,000 R's, each computed from 107 homework and scrambled final pairs. We could then make a histogram of the 1,000 R's. So that's what you're going to see on the next page. And here it is. It's just positive. And so what is this? These are all the scrambled R's. So this is the empirical, means experimental. It's going to look different every time. Sampling distribution of R under the null after 1,000 random distributions. So we're calling it after 1,000 scramblings. Not random distributions, excuse me, after 1,000 random scramblings, randomizations. And this right here, this was our sample. This was our actual sample. We didn't get this one by randomization. We just want to know how different it is from the ones we get by scrambling. So this is the one we actually got. This is the one we really got, not through randomizations. It's this. And we're saying, hey, does it fit in with the other randomizations or does it look different? And what's our p-value? Our p-value is the percent of these scrambled R's, the percent of them that are as extreme as this one or more. And in this case, we got 0 of them. That's because the area beyond this area is 0%. We didn't even get one of them. That says 0% of the randomizer. 0% of randomizations yielded an R greater than equal to R's. So let's do it on the computer and we'll see. I mean, here's after 100,000 randomizations. Okay, we finally got one. Look at this, we got a tiny little bit right there. Okay, so now the p-value went up a tiny bit. It doesn't have to. That's because we did happen to get, just by the luck of the draw, right here. But it's basically the same thing. So this doesn't always happen. The p-value, that's the p-value, may go up or down may go up or down with more randomizations. One thing that will change is you get a smoother curve. Sorry, I'm talking and I didn't look here. I'm sorry. So it did, you see how, what I'm saying is, you see right here, it went up a tiny bit. So I don't know if you can see, but there's a tiny bit of the curve that extends there. It's so hard to see. So it's the same thing. But this 0.1% refers to, I can't even see it, but there's a tiny part from this way is 0.01%. Okay, so let's go to the computer. I can show you. I think it's prettier to watch it. So let's go over to the computer. All right, and let's do this. Okay, so here's final right now, and I'll choose homework, and I click this re-randomization. If you want to see our chi-squared z statistics, our F and T, but here's our re-randomization. So, whoa, it's after 2,000. It says after 2,000. Now it's showing you R right here. And we didn't, watch this, we didn't get any so far. Now I'm going to click here and I'll get more and more. See if this changes right here. After 5,000 randomizations, not. Let's just keep doing it. Does it change? We might, oops, yeah, we must have gotten one or so. See, it's smoother and we did a tiny bit, but the p-value is almost 0. And you can do it, as many randomizations as you want. And you'll see this, whoa, we got it. And this is right here is our sample R of 0.3926. Okay, so you can try that yourself. Any questions on that? And now the next thing we're going to look at is now we're going to add exams, and we're going to do the same thing. So now we have 2 predictors, and here we have to do R, because we can't do little r, because we're in multiple regression now. And so we're only positive, and this is what it looks like. And we can keep doing more re-randomizations. And I doubt we're going to see anything because this is such a good model. Our R is very high here. So we're going to get a smoother curve, but I think P is going to remain 0. Now, theoretically, of course, if we did this forever, we're going to get there is some probability that they match up and we get an R that big, but it's very low. Okay? So let's fill that in our notebooks, and then we'll be done. Okay. So now what are we doing? It's a little bit harder to explain, but it's basically the same thing. Okay, so now we have multiple regression. And so our R is still that R in the population is 0. That's the same thing as both slopes. Those two are equivalent. Okay? Now, so what are we doing here? So here we have these are the actual homework and exam. The actual X1 is homework, X2 is exam. These are the actual pairs. And our actual sample observed correlation was between all 3 actual triplets, right? This is the actual final scores, right? And what did we get? We got this R, it has to be a capital R, equal to 0.6198. Okay? That's what we actually got. And we just want to see how that compares, how different that is from what? From if we take these actual pairs right here and match them up not with these, but with scrambled finals. So I'll just close my eyes, and here, let's say I got 68 here, and then 76, etc. And I scrambled them all the way down, and 70 here, let's say. Okay? So I match these 20 with these already. I don't scramble these up because these are X variables, and we want to see how well they're predicting that, these two. So we keep these together, and now we're just saying, hey, the null is that this gives us no information. Even if I have both of these, it gives us no information about what final. So I might as well just scramble them up, and just by the luck of the draw, just by chance, I will get an R that big. And if the p-value is really small, we reject it. Well, now we're just creating our own distribution. So we don't have to do any assumptions, and it's so much fun to do this. It's so easy to do this with today's computer power. Okay, so here what we're doing now, what this is the actual X1, X2 pairs and random scrambled finals. Okay? Does that make sense? All right, let's see what we got. So after 1,000 randomizations, this looks just like what we did on the computer. After 1,000 of them, I know, sorry, I'm going to get you dizzy. It's like you're on a boat or something. Sorry. Okay, so here we go. Here's our observed one, right? That's our observed sample R. It's not a critical value or anything like that. It's just our observed sample R equal to 0.6198. And look that we really got, not through randomizations. How does it compare to all our randomized ones? Well, it's really, really different. The p-value is clearly 0. We didn't get anything close. Our observed sample is very different than ours we'd get by chance. by chance. Very different. So we reject the null. Okay? Extraordinarily strong evidence that there's something in our model. Okay, and here it is again. It's just smoother. After 100,000, you get smoother. So it is again. Again, that's R. So that's pretty much it. That's the idea. And these there's a lot of computer simulations you can do to, instead of parametric statistics. This is just one of them. All right, so how does this compare to the F and chi-squared test? Well, it's really hard to compare them, but in general, the randomization is the most conservative because it has the least assumptions. But that's not always true. So let me just zoom out a little bit, and I'm sorry I'm giving you a headache here. Okay? In other words, it requires the strongest evidence to reject the null. But this is very iffy. I wouldn't quote, look, I wrote it in the book. I say, don't quote me on it. I probably should take it out because it's very hard to know. What you want to do is use as many tests as you can. This one doesn't depend on all those assumptions. Since your assumptions are always going to be violated, it's great to do the parametric test, do the F, do the chi-squared, and then do this. And if they disagree, then something really screwy is going on. Just about all the time they'll agree. But if they disagree, you have to get to the bottom of it. It would be very interesting. And you should show me if you come across that, and we can figure out what's going on. Okay? But if they really disagree, they'll usually agree pretty strongly. All right? What's the downside of the randomization test? It's that you don't get parameter estimates for the model. You don't get those slopes. All you get is a significance test for the overall regression effect. You can't separate out the effects of homework, exams, etc. So you don't get slope estimates. So that is a disadvantage. But to test the strict null, it's really great. And so what I strongly recommend is to just use whatever you have in your toolbox. And this is a great method to make sure you're doing things right, because you can see the strict null being enacted. Yes, any questions? Okay, and so we're going to be doing more of these kind of non-parametric tests, and it will just add to your toolbox along with the parametric tests. So have a great Halloween, and I'll see you on Tuesday.